Okay, so we're back talking about section 2.6, the 10 basic shapes, the 10 basic graphs. And on the last video, we got through the first 8. The first 8 are the function graphs. We can say f of x equals. We know the vertical line test works on those, and we're going to use the shifting rules on those in the next section, actually. But we need to finish up talking about the last 2 shapes. So if you follow along with me, we have 2 non-function examples. So graph number 9, x equals y squared, is an example of something that is not a function because the x would repeat. Now, how do we put that in our calculator? Might be another question for you. It's different, you can tell. It's got the x equals instead of y equals, for one thing. You could turn it around and say y squared equals x like that, and then to solve it, you would square root it. Well, when you square root it, there's a plus and a minus. You remember that from back in chapter 1? When you take the square root, you have to say plus and minus at the other side. So if you were using your graphing calculator, you would graph in one line, square root of x, and then in another, you would graph the negative square root of x. So try that on your graphing calculator and see what that looks like. So you should be seeing a sideways parabola, or a horizontal parabola, more particular. So it's shaping the 1 square root of x, which we learned is the arc shape, but then the negative is turned upside down. So when you put those together, it makes a horizontal sideways parabola. Now, if we were just doing the old style point plotting, which you know I like to talk about that, we could plug in, probably on the y side easier this time, we could plug in, say, 0. 0 squared gives us x is 0. We could plug in 1. 1 squared, x equals 1. If we plug in negative 1, negative 1 squared is also x is 1. There's that repeated x we're not allowed to have in functions, right? So when the x is repeated with 2 different y values, certainly not a function. Also, we can see it on the graph. At x is 1, we have a positive and a negative output. The vertical line would hit it twice. That's why that thing is not a function. It's still a fine graph, but we're not going to focus on it as much because we focus more on functions in this algebra class, but it's to be aware of. So it does have domain and range. The domain is 0 to infinity. It starts at 0, goes to the right. The range is the infinity this time. So it's almost like the other ones, just things have been flipped around. You know, it's obviously still a parabola, but it's on its side. All right, the other graph that we're going to talk about, number 10, x equals absolute value of y. Sort of the same argument here. It winds up being sideways again, and it's the sideways v. You might remember the vertical function one was y equals absolute of x, made the upright v. So when it's x equals absolute value of y, and we can derive some points and see that that's so. So it is not a function again. While we're here, I would like to go ahead and mention a symmetry thing. Since these 2 non-functions are looking at us here, I'd like to talk to you about their symmetry. These would be examples of x-axis symmetry. That's going to be in the next section, so I'll mention that again. But while we've got these, notice that they're symmetric with the x-axis. If we were to fold these graphs along this x-axis, if we had a piece of paper, which you might, and folded those curves together, creased it right there, this and this curve, they'd come together. That's symmetry. So we've got symmetry on the x-axis. Same thing here. If we fold it together along this x-axis, those 2 parts of the graph would meet up. So symmetry with the x-axis can never happen with a function. So there can't be a top and a bottom that matches up, you know, with any of the function symmetries. So again, I wanted you to see that. I also want you to know the official way to tell if something's symmetric with the x-axis is if you can make y negative y and it doesn't matter. Like you get the same output for x. And you can see that's true here. If y is 1 or if y is negative 1, it does not matter if y is positive or negative, you get the same result for x. Same thing here. Y can be a positive number or a negative number. We can tell it with our t-table. If we plug in y is 1, we get x is 1. If we plug in y is negative 1, we also get x is 1. And that's how we prove x-axis symmetry. The y can be positive or negative and get the same output. All right, The last thing on this handout for 2.6 that you'll be doing in your homework is talking about whether a function is increasing, decreasing, or constant. So I'd like to plug in or show you another type of graph or another graph to use as an example and talk about is it increasing, decreasing, or constant. Okay, so again, that's increasing, decreasing, and constant. So if you have this question in your homework, it's referring to the slope of your graph. Now, if you're doing a line, like a linear equation, like let's say y equals 3x plus 1. That's a linear equation with the slope of 3. Well, obviously, the slope is positive 3. So we can say that thing is always increasing. The slope is always increasing. It's increasing from negative infinity to positive infinity. All the time it's increasing on the domain of that. So the line is a special case though. All the other graphs, the other 9 graphs that we've studied have some sort of other thing going on with them. So they're not just that, like the line. For example, our parabola. Let's say we have y equals x squared. Our parabola shape, its slope is all over the place. It's not got the same slope all the time for sure. You know, it's curving around, sometimes taller on this side, less slopey, and then it comes down, turns around, and then it's a different slope over here. So its slope is ever changing. What you'll do, because if you just look at it, you kind of might say, hey, this thing looks like it's going up, it's just positive. But actually, with further investigation, if you lay your pencil or a marker on it, that is a positive. If you set a line, it's a positive line. We put our pencil or marker next to a point along its curve called a tangent line. So you touch a point on that curve and you say, what's the slope of that? What's the slope of that line? Well, that's a positive. But if I put it on this side, you see, that's a negative slope. This is considered, if you're reading from left to right, it's going downhill. That's a negative slope on that side. So we would say this side is decreasing while this side is increasing. And in your directions, it will say, name the interval where it's increasing, decreasing. Constant means it's flat, 0 slope, on the domain in reference to the the x-axis. So looking at it this way, as x's perspective, this would be negative infinity up to the x value of 0. It's decreasing from negative infinity to 0. And it says open interval, so just use a parenthesis on all of these. And then increasing would say starts at 0 and then infinity. And that's how we'll designate those. Let's see, what's another example? Let's do our x cubed graph. Y equals x cubed. What do you think about that one? Again, it's kind of hard to tell just eyeballing it. I think it's best until you get real used to this. Put your pencil on it or a straight edge and say, what's the slope? Is it going uphill from left to right? That is uphill. Any point along that curve, even over here, that's still positive. Any place I put the marker, any point you can find along that curve, it's always positive. So I would say it's increasing all the time, negative infinity to positive infinity. Now to make it more interesting in your homework, they draw you some piecewise functions. So maybe something like this. Put a few graphs together. So you have something to go on for the constant part of the slope. So let's say this is the -1 on the x, and let's say that's 3. So if we were to list, and feel free to pause the video here and list where it's increasing, decreasing, and constant. We would say this part, that's a negative slope. So it is decreasing from negative infinity up to this x value where it turns around at -1. Then it's constant. Constant means it's a 0 slope, flat, from -1 to 3. And then this is where it's definitely a positive slope, so it's an increasing part of the graph from 3 to infinity. All right, so let me give you one more to try. Let's see what we can do here. Let's do this. Let's make it flat, and then let's make it a parabola. And let's let it turn around. I'll tell you the turning points are at -3, and let's make that 2. And then tell me the increasing, decreasing, and constant part of this graph. So this part is definitely a positive slope line. So I will say that's increasing part, negative infinity up to -3. So for this section of the graph, that's a positive slant. And then I meant to make this nice and flat. I don't know if you can tell that, but that's my constant part of the function from -3 to 2. And this is kind of the exception to the rule. We just use parentheses for everything. Per the direction, it'll say name the open interval. If it says the word open interval, that means don't use a bracket. Don't include the endpoints. Just the open interval is inferred. And then it's increasing again. Notice this parabola shape. That's a positive slant on it. So it's increasing again. So we might just say union at 2 and then on over. And that's how we could designate that. So we didn't have any decreasing part on that one. All right, I hope that helps. So that concludes our information for, I'm always losing my little clicker here. That concludes our information for section 2.6. As always, feel free to reach out if you have further questions.